15, 1.3, 1.1, 0.9, 0.4.
Make sure once you've got your numbers in here that you add units
Okay.
to the things.
Average luminosity.
Originally, we had this crazy idea that we're going to give them lots of parameters for planets and have them pick the ones that would be the most, let's say, suitable for life, and that would have gravitations between a certain theme, and they'd have to do research to figure out what those were. But then we ran out of time, and plus it got more interesting when we just told them to make it up. So we had them create all the parameters. We had them do some background research so they would understand what would be reasonable values. And so I like the direction that took, because it's important in science and in math to make sense of numbers and to know what are good numbers and what are bad numbers. And so the fact that we didn't give them any parameters made them have to do that background research and really make choices that really compared orders of magnitudes of numbers and tried to understand why some numbers are appropriate and some numbers are not. Okay, and then whatever numbers they had, that's what we did the calculations with. It also created a situation where every team had different numbers, so they couldn't cheat. So I like projects that result in products where all the solutions are different, but similar enough that it's easy to give feedback, so they're not all over the place. What did we do to the distance in that problem?
We squared it.
No. No, what was the change in the problem? Do you remember?
Oh, half.
So what was changed? The masses, the distances, what's going on? So what are we going to replace that D by?
0.5 squared.
0.5 D.
Oh,
So we'll put that in.
why would we square it?
We're about to.
Okay.
I'm just replacing the D. 0.5 D, the whole thing squared.
Oh, okay.
So when I simplify what's in the bottom, what do I get?
0.25.
And then here,
D squared.
you see how this
20.
looks
Oh,
like
that's
this,
not 20.
which equals this.
40, 40, 40.
So we can replace that by 40. So
Okay.
now you need to just figure that out.
Thank you.
They have a hard time differentiating between their focal points and their center points because it's all something completely new, especially since you're using the same point for different things. We're using the star as the center of a universe. So you have their habitable zones, which are basically concentric circles that are based around the star as the center. But then, because the star is also a focal point of the ellipse, it becomes something different. So now your center has moved, and you have some ellipse that's going around that star. So yeah, the distance from the center, like if this is the center of your ellipse right now, it shouldn't be. This should be shifted over, so this is one of your focal points, and then the center gets shifted over. Okay. And the distance between that star and the center should be your C.
I think I just moved it because it looked wrong, but it's not wrong.
Okay.
Okay. So I'll make it real. It's just that it went really big, and I thought it was wrong because I saw everybody else's was like really small.
Maybe because they were zoomed out already. I don't know.
Well, because it went all the way to like 200 and something.
Yeah,
Okay.
it will be. It's
I'll show
big.
it to you tomorrow.
Okay.
Where they were struggling with the most on my content was really the stuff that dealt with the process skills and them explaining why they made certain decisions they made in the project, why a star is habitable. If you're going to say this characteristic's important, what does that do for life? And not everybody was able to answer that question. And I was surprised about that because a lot of times when I was grading them on putting down a characteristic, I wouldn't allow it if they didn't justify the response. That is a good description of the habitable zone. I want you to just kind of touch on, once Ellen has all the orbits, what that means.
Yeah, I don't have that because he's not.
Okay, so you'll finish that when he's done, because for some of the orbits might be too close to your star, so you'll know it's too hot.
Yeah.
Some might be too far, so you'll know it's too cold, but that's a good start. So I'll give you like partial for that, and almost full credit for that one, just add another characteristics.
Okay.
Yeah.
For life or for the planet? For life.
For the planet, like what are some conditions on the planet that will help it so that these things can happen? Yeah.
We drew a two-dimensional universe, so it's a flat universe. But real universes, it would be 3D, so you might have one planet orbiting this way and another planet orbiting this way, and all kinds of different orbits. You're not proving that something's going to stay in a certain orbit because of something. We can ask them questions about it in the presentations, but the actual product that they have, it's not completely clear, and that's something that we'll probably refine for the next time we do it if we do this project again. One
team wanted to base their solar system on ammonia. We almost went there. I just couldn't find the right equations to recalculate the habitable zone. And then by the time we got further along, I think we just lost interest. We just got so into it that we dropped the ball on that one. But that'll be something that I'll have to keep on my back pocket for next year if we revisit this project, is be ready to not give them the parameters for ammonia, but to teach them how they would recalculate where the habitable zone would be for something like ammonia that has much smaller boiling point than water.